Okay, so let's get some idea of what a manifold is. I mean, to be more precise, it's a hard idea. And as I said, you're not working on a single parametrization. You work with many parametrizations. You have to glue them. And so locally, every manifold is like Euclidean space, but globally it's not like if you take a circle and it's closed, it doesn't have boundary, and you cannot see this in it's a one-dimensional object. But if you are on the line, you cannot have an object that is one-dimensional and has no boundary unless it's the whole space. But this one is some, let's say, compact, and the whole line is not compact. So the global geometry is different, but we are going to do calculations, so let's ignore that. Okay, I will go very fast through vector fields because we are most interested in forms. The sound? Yes. Okay. Let M be a smooth manifold. Oh, okay. Let me define a smooth M and B smooth manifolds of the. Okay, so dimension of M is N, dimension of M is N. I didn't define what dimension is, but when I the space, the dimension of space which is parameterized on. And we say that no, this doesn't. I'll use this one. We say that f from M to N is smooth if for any charts u phi on M and v psi on N. We have the following. So we have u to R N, for example, Rm. V is to R N. This is psi, this is phi, and this is F, or a restriction of F. Some restriction of F. And we have here so we start from here and go in this direction. So this is psi composed with F, restriction to U maybe, and intersection with, I think, C of V, and composed with phi to the -1. So we are going that direction. We are going this, then this, then this. So if for any C composed with F with some restriction, doesn't matter, composed with F -1 is smooth. Let's ignore the exact domains of the maps. I think we have, okay, this is, so if this is f of u inverse, no, I will just ignore that. Okay. So if you have map between two manifolds, it is smooth if when you parameterize it, it corresponds to smooth map from Rm to Rn. And the space of all smooth maps is denoted by C infinity Mn. And if n is R, we define f of m to be C infinity of Mn. And this thing here, Fm, is an Euler algebra. And itself, it's a ring. So Fm, so this is a commutative ring with unity as well. So it's R algebra, so it's a commutative ring on itself, and I can multiply functions by real numbers. In the usual way, I will not define that, we just do this naturally. Now, let's give example. So, of a smooth map. So let's take M is S1. So it is xy such that x squared plus y squared is 0. And N is S2. xy z R3, not 1. This is 1. Such that x squared plus y squared plus z squared is 1. And now define the following function. Map a circle to the equator. So f from m to n, f of xy is xy 0. Of course, this is well defined because if x squared plus y squared is 1, then x squared plus y squared plus 0 squared is also 1. So this is a map. So we have like this is mapping. We are mapping this here. So this is m. We are mapping it to the sphere, we are mapping the unit circle to the disk. And so let's see how it becomes a smooth map. So take, for example, some, let's say U and V are, so U is in R squared, R, and V is in R squared. And P is not, let's not make phi, let's make this function alpha of is not a chart. So we have alpha from R okay, I'm just, U is a subset of S1 and V is a subset of S2. And I'm making parameterization R from R to U such that alpha of phi is cosine phi sine phi. and a bit better from r squared to maybe not from r, but from some interval. From interval minus epsilon, epsilon, let's say some interval, doesn't matter. B is from I don't know, some A, B times CD, some small numbers to S2 beta theta P is, what was this? Sine theta cosine phi, sine theta sine phi, and cosine theta. And then we have that B of when theta is 0, no, when theta is P over 2. B of P over 2 phi is cosine phi sine phi 0. And this is exactly f of cosine phi sine phi. And this is exactly f of, this was alpha phi. Like that. So what we made some, let's make some diagram here. So we have U, and we go by alpha to the -1 to R. Not to R, but to minus epsilon, epsilon, some interval here. Not that, no, this is not good. Let's make it the EF. This is make it the EF. This is some numbers EF that has to be determined later. And here we are going from EF to, let's say, A times AB times CD. Is it right? So this is B of P2, and the second argument is not fixed. Here we have V and go to A, B to the minus, beta to the -1. And here we have F. So we have F if we go there and there, so we have F composed with alpha is the same as beta composed with, is that right? Beta. Okay, so we are fixing, no, we are going here, this is map X, where X of phi is P over 2 phi. So we have F composed with A is beta composed with X, which is equivalent to that diagram. when, so this means that f composed with f is decomposed with x alpha minus 1, or alpha minus 1 composed with f, sorry, bit, is x composed with alpha minus 1. So here, if we multiply by alpha right, and here we multiply by beta minus 1 left. And we're getting this diagram. So beta minus 1 composed with f is the same as x composed with alpha minus 1. And this was the same as the definition. So so u alpha minus 1 and v beta minus 1 are the charts. So usually in manifold theory, everything is defined in terms of charts, but it's much easier. So usually in manifold theory, everything is defined in terms of charts, but it's much easier to work with parameterizations, because parameterization starts from real numbers and go to the surface in some sense, and to go from to the surface to the coordinates is a bit harder. For example, if you are given point on the sphere, how can you find theta and phi? It's not that easy. But if you're given theta and phi, you just use sines and cosines and locating on the map on the sphere. Okay, now we have some idea what smooth functions are. Let's define a vector field. So let M be a smooth manifold. Then a vector field on M is a smooth map. It's it's an operator x from Fm to Fm. So these are, remember, the set of smooth functions on M, such that for any f and g in Fm, so okay, x of fg is x of f times g plus f times xg. So this is condition 1, and condition 2, x is R linear. This means it's linear with respect to the real numbers. This is called Leibniz rule. So let's give example. M is real numbers, and x is d dx. We have d dx of fj is df dx times g plus f times d dg dx. And for m equals Rn, we have and I is from 1 to n. Arrhenius integer. We have example x equals partial derivative d dxi. Again, the Leibniz rule is satisfied. You know this rule from calculus, and this is a generalization. Now for curved manifolds, it's hard to define vector fields, and we will not need that. We will need mostly to work with forms. So I will not give examples because it requires more calculations. So now let's give the most important fact. So let's say theorem. Okay, let's do some small proposition. It is very easy proposition. So let M be a smooth manifold. And Xm be the set of space of vector fields. Define multiplication scalar, let's say scalar in brackets, scalar multiplication some symbol star, no, not star, let's like some, I need some operator. Usually people don't use any kind of symbol for multiplication, but this is from Fm times Xm times Xm by, so F times X of G is F times X of G for F and G in Fm and X in Xm. So you can multiply a function by a vector field, and what this means, when you apply the vector field at the function, you just copy the function and apply the vector field to the function. Then Xm is an Fm module. So that's why I did all the theory for modules, because here is a starting point for algebra on manifolds. And I'm not going to give concrete example because I'm going to give a theorem which gives all the possible vector fields. So I have the following theorem. Let n is of dimension n, and n is a smooth n manifold. Then, and U P is a chart on M. Then on M. Then, so let's, what this means, so This means that f is from U to Rn. Then f of u, not of u, x of u. So when we restrict to the, not the whole space, but restriction to the subset, x of u is n-dimensional fu module with basis d dx1 d dxn in local coordinates. In local coordinates. The local coordinates are the coordinates defined using this map. I mean, I'm not very precise about what they are, but we'll do some calculations with them later. So any element x in xu is represented by x is f1 d dx1 plus x fn d dxn for f1 fn in x of u. Okay. So some example. Yes. Yes. It's the, for example, the Eulerian vector field in Rn. So let's say in R2, doesn't matter. So x is x d dx plus y d dy. And you are used to a vector field. So if I have the plane here, to this point, for example, I give this vector. To this point, I give bigger vector, and so on. To this vector, I give this vector. To this vector, I give this vector. To this vector, I give this vector. So this is like some spreading out. So vector fields are usually this is like the basis, and if I get point, for example, 1 1, this is the vector 1 1. If I am the point 3 0, the vector is 3 0. That's starting from this point. Okay.
We can call just dx I e y.
Sorry?
We can call dxy e y.
Yeah. Yeah, but because it's applied to a function. So, okay, let's say x of f is given by x times df dx plus y times df dy. This is the definition of application. So this is differential operator for f in f r squared. Okay. Now let's give forms. So let M be a smooth manifold. The space omega bullet M, which is the exterior algebra of the dual space of M, is the space of differential forms. So this is the dual algebra, and we take the exterior power. So if n is the dimension of M, and we have basis local basis dx1 dxn, its dual basis, this is of x u is subset of M. The dual basis of xu star, which is omega 1 u, is denoted by dx1 to dxn. So we are used to these symbols as some symbols in platesimals without precise meaning. In differential geometry, they have precise meaning. So we have dx I of d dx j is delta ij, is the Kronecker symbol by definition. So this is 0 if I doesn't equal to g, and 1 if I equals to g. And in g from 1 to n. Okay. Now let's repeat what we did few lectures before, do it for forms. So in R, for example, in R2, we have omega 0 m is set of functions. Omega 1 n is the space fx dx plus fy dy, where f and g are smooth functions. So m equals R2. And omega 2m is the space f dx which dy, where f is fm. In 3D, in n equals R3, omega 0 of m is f of m again. This is always the case. Omega 1 of m is the space fx dx, fy dy, plus fz dz. here three functions x, fy, fz are smooth functions. Omega 2 are two forms, so these are fx dy dz plus fy dz dx plus dz dx plus fz dx dy. Again, fx, fy, fz are fm. And omega 3m is the space f dx wedge dy wedge dz, where f is a small function. And this is the same as for Rn, which I did, but here we're not doing basis of vectors, but of differential forms, and the base ring is not real numbers, but the space of all smooth functions. And now let's define the exterior derivative. This is some kind of definition theorem in one sentence, but let M be a smooth manifold. The space the exterior derivative d from omega bullet m to omega bullet m, which is a graded map. So it's dp from omega pm to omega p plus 1n for p from 0 to n minus 1. N is the dimension of m. Is the unique linear map R linear. So it's linear with respect to real numbers, but not with respect to functions. That satisfies the following. So first, the 0 of f is df dx1 times dx1 plus df dxn times dxn. This is derivative of function. So f is omega 0n. This is like the gradient. These are the components of the gradient. And 2, if omega is a p form and eta is a q form, then d of omega wedge eta is the omega wedge eta plus minus 1 to the power of p omega wedge d eta. And 3, this decomposed with d, so d plus 1 composed with dp is 0. This means that it's omega, it's a cochain complex property. I'll have time for 2D and 3D. So this is written the last. So we have omega 0 d0 omega 1 and so on to omega, this is dp minus 1, to omega n. This is d1 and so forth. So maybe I will have only time for 2D. M is r squared. Okay. Now d0 of f is df dx times dx plus df dy times dy. So this is like gradient. d1 of fx dx plus fy dy, fx dx plus d1 of fy dy. And this is so this is I use this is the graded Leibniz rule. Graded Leibniz rule. Now this is d1 of fx wedge dx plus so fx of d dx. Here, this is the first argument, and the second argument is this is d2, d1, and the second argument is d1 of fy dy wedge dy plus fy d1 of dy. So this is 0 by definition because d of d is 0. These are 0. And the rest is we're going to this is d0. So we're going to use the previous. So this is the fx dy plus dx plus df x dy the whole wedge with dx. This is the first, and the third one, so the second and the fourth are 0, is dfy dx times dx. So partial df y partial dy times dy, and the whole wedge with dy. Okay, this with this is how much? Dx with dx is 0 because anything with wedge with itself is 0. So we have dy with dx, but this is minus dx dy. So this is minus dfx dy, and here we have plus df y dx times dx wedge dy. And this is used in Green theorem, if you recall. How it's called? Scalar curl or something like that? How do you know it? So this is curl in 2D for Green theorem, which we are going to do next. I'm going to show all the theorems in one. I'm going to do next. I'm going to show all the theorems in one. Next. I'm going to show all the theorems in one. So all the theorems from analysis which relate integrals two integrals on the boundary are single theorem and manifold theory. Stokes, divergence, gradient, Green theorem. Yeah. Okay, so we don't have time for 3D. We're going to do it next lecture. Sorry for being too fast, but there is no time to discuss. But this calculation, you can check them. You can check them themselves. They are not that hard. They're just using these three rules. We are doing these computations only from these three rules, and from the fact that dx wedge. So from v equals v0, from v minus w wedge v. We are using only these two rules, these rules and these rules. Can I delete? Oh, I forgot to end the stream. Now it's fine.